So what is the definition of process? The definition of process is, it is the path followed, it is the path followed when undergoing a change of state. When undergoing a change of state. When undergoing a change of state. So let us look at backward. What is change of state? Change of state is when any one parameter, when even one parameter of the system, any one property changes, then we say that system has undergone a change. When none changes, we say system is not undergoing a change. A system is in a definite state. Even if one of them is changing, it is clear, then we say system has undergone a change of state. Now when this system has undergone a change of state, it will follow a process. I'll give an example. It may not be a very correct example, but it will make your things clear. See, when we were a child, okay, we were maybe, I don't know how many grams child, maybe 3-4 kg will be, 5 kg I think is the weight of a child. But remember one thing, the temperature or the body temperature of the child was what? 37 degrees. Today, if suppose the child has become as big as my son, 28 years old, his weight may have increased to 100, that's a different thing. So there's a change of state. One property of his change, what is it? His weight changed, is this clear? But one thing, throughout this change in his life, there was a change in the mass. There was a change in the volume, because the fellow has grown up, his volume has changed. But throughout his lifetime, the temperature remained the same. So we say that's a process. A change is taking place. While a change is taking place, that change is taking place while something else is constant. Is this clear? That is process. The process in wave is the path followed. What is the path followed? So obviously we have got what? The first is isothermal process. Isothermal process. And the other one, generally the popular question that they ask is, differentiate between isothermal process and adiabatic process. So what is the isothermal process? So this is the second one. Isothermal process is a process. It is a process in which temperature is kept constant. Temperature is kept constant. So what is adiabatic process? Adiabatic process is a process in which the boundary is diathermic. Okay. Since the boundary is diathermic, temperature is kept constant. Second point that we have is, how is the temperature constant? Because there is exchange of energy. There is exchange of energy. Exchange of energy is heat, remember that. We don't say exchange of heat. You need to say exchange of energy nahi hota hai. So there is an exchange of energy from system to surrounding. And vice versa. Okay. Here what is happening? The temperature may change. In adiabatic process, what happens is the boundary is diathermic. The boundary is diathermic. Boundary is diathermic. If the boundary is diathermic, what is going to happen? There is going to be no energy exchange. There is no exchange of energy from system to surrounding and vice versa. From system to surrounding and vice versa. Just a minute. No, I kept the window open because I can get fresh air. But what will happen is it will affect the quality of recording. Okay. So there is no exchange. So if there is no exchange, temperature changes. Temperature changes. It is clear. How does the temperature change? Okay. If it is adiabatic expansion, this is the entrance exam question. If you see the textbook, this is not given, but I am explaining over here. Adiabatic expansion, temperature decreases. And adiabatic compression, temperature increases. So this is how the temperature does not remain constant. Okay. So obviously what happens? Delta T is equal to 0. Here delta T, change in temperature, not equal to 0. Now fourth is delta U. See, U stands for internal energy. So what is internal energy? Internal energy, we study in great detail what is internal energy at a later on date. Just maybe next lecture. So we just say internal, to start with, to put it across to you, internal energy U is a function of temperature. So if you say delta T is 0, delta U is 0, delta U is not equal to 0, because there is increase in temperature or decrease in temperature. So this was the first two process. One is isothermal, where you allow the exchange of energy. Okay, changes are taking place, but exchange of energy is allowed. The other is you just surround it with something like in some insulator. Diathermic boundary means what? It's insulator. What is going to happen? Exchange of energy is stopped. So what will happen is energy will remain inside. That can cause increase or decrease in temperature. We have is third one is isochoric process. So what is a isochoric process? Isochoric process is a process in which volume remains constant. Now what happens is, what is an example? I'll tell you, because I have to give you this example because in the numerical they will give this sentence that the combustion of benzene was done in a bomb calorimeter. Normally, if you see in your textbook, they have said combustion of benzene was done at constant volume. Calculate the enthalpy change at constant pressure. So then it's a very straight question. You can answer. You will be able to answer when I teach you those concepts. But if they just twist, instead of saying constant volume, if they just put the word bomb calorimeter, you will have a trouble. So what is this bomb calorimeter? What is bomb calorimeter? So bomb calorimeter generally is used to find the flash point. It is used to find flash point of fuel. What is flash point? Flash point is that temperature at which a fuel burns on its own. This is a very common problem, I'll tell you. Now, where we are, I'll give you an example. Now that we have time, I'll give you an example. See, for example, I mean, in pesticide companies, they make this um, emulsifiable concentrate. So, pesticide, what they do, say 35% of the pesticide is dissolved in 100 ml of, 35 grams is dissolved in 100 ml of naphtha. Naphtha is a sort of kerosene, if you will. And then they put what do you call emulsifiers. So it's called as a emulsifiable concentrate. So what do the farmer do? Farmer takes that one small tin of 100 ml, break open, and then he'll put into 10 liter of water. You can't sell pesticide in emulsified 10 liters. Now it becomes very difficult to transport. Now here, when we are preparing this pesticide, whenever the naphtha comes from the refineries, we always check the flash point, because India is a very diverse country. You have got Ladakh, which is, I don't know, -13, -14, God or what minus they are talking, we also don't know. And at the other extreme, we have got Rajasthan and Tamil Nadu, very close to the equator. Nagpur, for example, in Maharashtra, temperatures can reach 45. Summer temperature can reach 45. Suppose if you are keeping the tin at 45, if it bursts into flames, it can be a problem. So therefore, we always check, is the flash point more than 45? Highest temperature we think is 45. Nagpur reaches that temperature. So we always check, because we don't want the pesticide dabba to start burning. That is why you use dabba inside the dabba, not the dabba. The pesticide inside the box, inside the container, should not start burning on its own if it gets little air. Flash point. So that is burning at constant volume. Burning at constant volume. I'm telling the application. This is beyond the textbook, but I sometimes think thermodynamics little bit, it's always worth it. Otherwise, you'll never understand what is this going on. So what do we do in a bomb calorimeter? It's basically, you have a cylindrical vessel. You have a cylindrical vessel in which you put the fuel. Okay. You have a lid and you have a thermometer over here. So this is thermometer. Thermometer. So that thermometer is continuously measuring the temperature of the vapor, because the vapor will catch fire. Remember, as the temperature rises, that fuel will become vapor and the vapor will catch fire. Is this clear? And that temperature is called flash point. On its own, no spark plug, no lighter, no. Now as I was telling, listen carefully. Listen. So what happens over here is, you have a plate like this in which you have a candle. That burning candle. Actually, it opens like this. It opens like this. And there is a burning candle. Okay. So every time there will be a button, you press it, the candle will come up. And as the temperature rises 1 degree by degree, whatever, you press it, because of this trigger, it burns. So the temperature at which the vapor starts burning, you know that is its flash point. So when we talk of isochoric process, it is in which, when does volume remain constant? When you are doing a chemical change at constant volume, especially combustion. If you are doing combustion at constant volume, that instrument is called as bomb calorimeter. Okay. So if in the numericals they say that the combustion was done in a bomb calorimeter, it clearly means that combustion was done at constant volume. The fourth one is isobaric process. So isobaric process means what? It is a process in which the pressure remains constant throughout. Pressure remains constant throughout. Every day we are seeing at our house this happening. Your mother is cooking food in the kitchen. Is this clear? There is water evaporating while cooking. What is the pressure applied? It is atmospheric pressure. So most of the normal processes that we come across, are examples of what? Isobaric process, where the pressure remains constant throughout. Is it clear? Ice is melting. When ice is melting in a vessel, the pressure applied is what do you call constant pressure throughout the melting. Then when water is evaporating, water is boiling, all these processes which you see, so normally it will be a isobaric process. Then we come to the most important point, that is reversible process. So what is a reversible process? So first, before I begin reversible process, I have to explain to you that this is an imaginary process. Take this word now, I'll explain why it is an imaginary process. It's an imaginary process. So even though it's an imaginary process, why are we studying it? We'll understand when we come to the end of the story. So what happens in reversible process is, the change is done infinitesimally small steps. Infinitesimally small steps. Is this clear? What happens when it's done in infinitely small steps? So what are the characteristics of reversible reaction? The driving force and the opposing force. So suppose if I take a cylinder and a piston. Now that's why I taught you the whole concept of it. I am making the piston move by a very, very infinitesimally small, distance. So volume change is dV. Even this is very big, very small, at very, very small, infinitesimally small, there is a change in volume, because that change in volume represents work. For the piston to move like this was work done. The piston was moving up, the gas was pushing it, the volume was contracting and the gas was increasing and decreasing, work was done. But if the piston is moving infinitesimally small value of dV, then that is called reversible process. So in this case, what happens? The driving and opposing forces are infinitesimally different from each other. See, I am writing this as per the textbook, because this question they also ask. What are the characteristics of a reversible process? Then the second point, what can happen is, this is the first point. We will take down all the state I'll put in a very simple way. By changing reversing the conditions, the process can be easily reversed. The process can be easily reversed. So that means what happened? You supplied a heat dQ, not Q. Q is a very large amount. dQ, infinitesimally small amount of heat. So the work done was dW. So it was work of expansion. By reversing the condition, by withdrawing the heat, what can you do? Compression can take place. Because it is at equilibrium. It is at equilibrium. That is what they are saying. So you supplied a heat dq, dW is the work done, not W. W is a very large value. dW is infinitely small. So if you withdraw the heat, you are able to withdraw dq. Withdrawing heat dq is very, very difficult. It is impossible, not possible. So then the work of compression of the minus dW or plus dW will be achieved. This is clear. Every step, at every step, the process is in mechanical equilibrium. What is mechanical equilibrium? When pressure of the system remains constant. I told you equilibrium are three types. Mechanical, then we had chemical, and then we had, so chemical, I said composition does not change. Is it clear? Mechanical means pressure remains constant. At every step, the process is in mechanical equilibrium. That means the pressure will remain constant. The fourth point that they have said was one point, that is maximum work is done. Why we have to study? Process takes place since the process takes place in infinite small steps. In infinite small step, the system is in equilibrium. System is in temperature and pressure equilibrium. At all steps. At all steps. See, what are we trying to say in all this? I'll give you a simple logic. Exam. When you write an exam, one person gets 25 marks, another gets 35, another gets 40. Now, how do I judge who is really studying? It is clear. For that, what happens is we set a paper, we set a benchmark that this paper is of 100 marks. So, moment you set a benchmark that this is the level you have to achieve, and then 25, 40, 45, at least the person who has got 25 we know has failed. Then all the process will start now calling up parents, this, that and all. We are trying to benchmark and understand. So exactly the same way here what happens. We know that engine is doing work. Petrol engine or diesel engine, heat engine is doing mechanical work. How? By converting heat energy into mechanical work by the process of expansion and compression of gas. Now, whatever work is it doing, we have to have an idea whether this work is the maximum that it can do. Because I told you, heat energy is not completely converted into mechanical work. This is the only thing which is against law of conservation of energy. In law of conservation of energy, we said that energy can be converted from one form to the other completely. Exception to the case is heat getting converted into work. So now we have to know how much actually this engine is supposed to do and how much mechanical work is it giving. So how much it is supposed to do, if you have a machine of that level, then why will use this stupid thing which is not giving maximum work? So what we do is we use mathematical principle. We use the principle of mathematics, derive an equation, okay, derive an equation that if this machine was working, if this engine was working in a reversible process, infinitesimally small step, the piston was moving 0.001 micron at every step, then it would have achieved maximum work. Now that we can't do. it will move straight, irreversible, na, from say 0 ml to something like 200 ml. It's going to just move. Is this clear? So that is an irreversible process. It is a irreversible. It takes place in large step. So in a reversible process, we mathematically calculate how much engine is supposed to do work, and for that calculation we have to consider a reversible process. That is why I said it is a imaginary process. It's an imaginary process because by considering mathematically, it is taking place in infinitesimally small step, automatically translates to maximum work, and that can be determined mathematically. So you know only two things. The volume was 0 ml, volume went to 200. If the gas changed, the piston pushed, the volume change in the cylinder was 0 to 200, putting in the mathematical equation, you will know how much work is supposed to be done. And factually you will calculate how much is the work done. So how much is the work done divided by what is supposed to be done, divide into 100, that is percentage efficiency. And from that calculation only I told you petrol engine is 38% and diesel engine is about 42% efficient. So in order to calculate how much is the capacity that this engine can work, we have to take into consideration reversible process. Because from the concept of reversible process, we will be able to derive the mathematical expression for maximum work to be done. And we can calculate how much work is being done. How much work is being done. How can we know how much work is being done? That is by considering irreversible process. Absolutely it is useful. So next is, sixth is a reversible process. So what happens in a reversible process is, it is not imaginary, it is an actual process. What happens in that? First of all, the change takes place in large step. The change takes place. It is actual process, not imaginary. The change takes place in large steps. The change takes place in large steps. The second point is that the system is in equilibrium. The system is in equilibrium only in initial and final step, not at every step. If it is happening at every step, it is reversible. If only initial and final state, then it is irreversible. Initial and final state. Then the third point is what? Work done is not maximum. Work done is not maximum. Work done is not maximum. Is this clear? So with knowing now these are the different processes, now we are going to use all these concepts in our study of thermodynamics. Somewhere we keep the pressure constant, so we say it's an isobaric process. Then what happens? Somewhere we are going to keep the volume constant, like we burn ethyl alcohol in constant pressure, that is in open, so atmospheric pressure is there. Isobaric process. We burn inside a what you call bomb calorimeter, then we know it is what you call isochoric process, constant volume. Then we find out how much is the heat that is evolved. Is it better to do it at constant volume or is it better to do at constant pressure? So these are all what you call calculations that we are going to come to using these concepts of reversible, all these processes. Okay, they start with work, and in work they are directly quoting first law of thermodynamics, which is wrong. Then we will first study first law of thermodynamics and then apply it to the concept of work. So we have the next topic is postulates of first law of postulates of first law of thermodynamics. So what are the postulates? Let us look at some postulates of first law of thermodynamics. The first postulate is energy is neither created nor destroyed. The law of conservation of mass. So first law of thermodynamics is another way of saying what is law of conservation of matter. Energy is neither created. Energy is neither created nor destroyed. Energy is neither created nor destroyed. Total energy of the universe is constant. Total energy of universe is constant. Okay. Then the third point, if energy of one form is consumed, it gives energy of another form, which is not true. So what is the drawback of first law of thermodynamics? That we are going to come as corollary. It is clear. So if energy in one form, if energy in one form is used, it forms, it gets converted, to energy in another form. In another form. Gets converted into energy in another form. Okay. Now the fourth, very good statement which people don't understand. It is impossible to make, see if this question is asked, it is impossible to make a perpetual motion machine is a statement of, the answer will be first law of thermodynamics. People will not understand. And what is a perpetual motion machine, we'll see. So it is impossible to make, a perpetual motion machine. It is impossible to make a perpetual motion machine. What is a perpetual motion machine? A machine which will do work without consuming energy. How can you have a machine which will just do work with, because what is energy? Capacity to do work. So if you say, okay sir, let us consider there is a machine which will do work without consuming energy. That means it did work. And capacity to do work is energy. That means it created work, no? Energy can neither be created nor destroyed. This will, be against the first statement that we have done. So this is one way of saying that if a work is creating, if a work is happening, it is consuming energy. You cannot have a machine which will do work. Machine does mechanical work without consuming energy. So if there is a machine which does work without consuming energy, that is called as a perpetual motion machine. And there is no such machine. Every machine requires some form of energy or the other. It is clear. Now what happens is, we now talk about the corollary to the first law. The drawback. What is not said in first law, which I have been saying from day one. Is it clear? The corollary to first law of thermodynamics is there is exact equivalence there is exact equivalence between mechanical work and heat energy. That means the opposite is not true. That there is no exact equivalence between heat energy and mechanical work. What is it that we are talking? What does this statement mean? See, what happened was Joule, he did an experiment. What did he do? He took a trough containing water. See, actually these are things which have to be taught in the lower standards as a part of science education. But I know for sure nothing is taught, everything is by hearted. And at a higher standard, what happens? So what happened was Joule took a trough containing water. This is a trough. It contained water. And this was a spindle. So he rotated the spindle. So when you rotate, and then there was a thermometer over here. There was a thermometer over here. So when he rotated, what happened? When he was rotating, remember the molecules of water are also moving kinetic energy, and kinetic energy gets converted to temperature. Kinetic energy is a function of temperature. So temperature of the water rose. Temperature of water rose means energy was created. Heat energy was created. So what did he realize? He realized that 4.18 joule of mechanical work, 4.18 joule of mechanical work produced a heat energy equivalent of 1 calorie. So which is the largest unit? Calorie is always the largest unit, remember that. So you have joules, erg, calorie and EV, electron volt, okay. These are units of energy. So between electron volt, joule, calorie and erg, calorie has the maximum value. Understand, that question has been asked. So 4.18 joule of mechanical energy created 1 calorie of heat energy. There is exact equivalence. So this is the experiment that he did. So he was able to, that's why it's called as mechanical equivalent of heat. What is this called as? Mechanical equivalent of heat. What does this tell you? That mechanical energy will get converted 100% into heat, but heat cannot. Heat will not get converted into 100% mechanical energy. So that's why this is there. 4.18 joule is equal to 1 calorie. Is this point clear? So this was about first law of thermodynamics. Now what do we, the story doesn't end. Now we talk about the mathematical expression for first law. The mathematical expression for first law of thermodynamics. Mathematical expression of first law. I'll take a very unconventional route to explain this. See, suppose we take a kettle. My diagrams are a little bad, so please excuse me. So suppose if I have a kettle, filled with water. So what happens? Now listen. Just little better. Okay. So your water in the kettle, water in kettle is system. Water in the kettle is system. So your kettle is the boundary. Isothermal boundary it's going to allow. Okay. Boundary is a part of the surrounding, remember that. So what are we doing? We are supplying a certain amount of energy Q first to start with. See, what happens is that water in the kettle had some energy which we call as heat capacity. If you remember, in your earlier given study, heat capacity and specific heat. I told you also, specific heat is intensive property, heat capacity is extensive property. So what was the heat capacity? mc theta, mass into specific heat into temperature. So mass of water in the kettle into temperature, say 20 degrees, this is 20 degrees, into specific heat of water is 1. So that was the internal energy already present U1. So U, internal energy is given by the symbol U. So that was the already present. Then what did you do? You supplied a certain amount of heat energy, kept it on a burner and heat energy. So the temperature rose. The temperature rose from 20 degrees to 100 degrees. So with this energy that you supplied, the temperature rose from 20 degrees to 100 degrees. Did you stop giving heat? No, you gave more heat. Further heat that you supplied, what happened? Went in first converting mass into latent heat. Went in converting the steam into liquid. Sorry, the liquid into steam. I'm sorry, I've gone crazy. So, convert the liquid into steam. And what did the steam do? What did the steam do? The steam applied pressure on the lid and the lid started moving up and down. This is what James Watt observed, if you remember. The principle was given by James Watt while he was making, he was boiling water in a kettle for his mother. And it was George Louis Stevenson who converted this into a steam engine. And that steam engine started the Industrial Revolution. That's why, when you study a subject, it has to be very conceptual, because it's not that James Watt got suddenly knowledge from somewhere. He was so much engrossed in understanding the effect of heat that it struck him that this is what is doing. The steam is doing mechanical work. Or in other words, already it had some energy. You supplied more energy. And then further energy that you supplied went into doing mechanical work. And what does this all lead to? The final energy present in the system, that is U2. Final energy present in the system, U2. So now U2 minus U1, I take this over here, will be delta U, the internal energy change, and that is equal to Q plus W. So this is the mathematical expression for the first law of thermodynamics. But here what happens? Remember, delta U is a state function. You'll say, sir, why is U a state function? And so why delta U is state function? See, I'll explain this like this. Suppose we have a graph. I have a system at position A with energy E1, and at a position B, energy is E2. There are two possibilities. U, not E. The older nomenclature, U1 and this is U2. This is internal energy. I am trying to prove that internal energy is a state function. What am I trying to say? Internal energy is a state function. How am I proving it? So this is proof of internal energy is state function. How can I say, suppose I change from this path 1, u1 to u2, and then I bring it back from u2 to u1 by a path 2. The first possibility is, in this case, path 1 is greater than path 2. So whatever was the energy absorbed, the same amount of energy was not released. That means, what are you trying to tell? That it went from here to here, energy was destroyed. Energy was destroyed. If path 1 has a greater energy than path 2, that means energy is destroyed, which is not possible. Energy is neither destroyed nor gained. What is the other possibility? Path 1 is less than path 2. That means you supplied more energy over here. While coming back to the same position, it lost some energy. No, it created energy. Energy was created. So both these thought process is wrong. So there is only one possibility, and what is that? That energy change during path 1 is equal to energy change during path 2. So if from this to this and this to this, the path, whatever path is there, the change is irrespective of the path. The change in internal energy is irrespective of the path. What does it tell you? It tells you that delta U is a state function. Okay, if delta U is a state function, but Q is not a state function. Q is a path variable. Q and W are path variable, that's what I have to tell you. If Q is a path variable, then what is the sign function that sign convention that we have? The sign convention, if Q heat is absorbed, then Q is taken as positive, path dependent. If you just say heat, I have to ask you, is heat absorbed or heat evolved? Both the case, the values are, there is a plus sign or a minus sign, path dependent. If heat is evolved, then what happens? Q is negative. Then work of expansion. For a cylinder, gas piston is the story. So work of expansion, work is negative. Work of compression, work is positive. So you can see Q is not a state function, W is not a phase function, but Q plus W will be delta U, the internal energy change that is happening, and that is a state function. So they will give you, see, they will say delta U state function, Q state function, W state function, then Q state function, this is not state function, like that they'll make 4 alternatives. So you should remember, in the first law of thermodynamics, mathematical expression, the internal energy change is a state function. I explained to you why is internal energy a change a state function. But Q and W are not state function, they are path variables. They are path variable. And what is the sign convention? If heat is absorbed, Q is positive. If heat is evolved, then what happens? Q is negative. If work of expansion, then work is negative. Work of compression, work is positive.